So, okay. So I recall my request. Now let's start. So I'm sorry, maybe for some people, the first lecture will be very elementary, but nevertheless, I would like to start from the very beginning. So the first topic is some reminder on associative algebras. So the base field is arbitrary. Let's suppose C or any field. Characteristic 0. And what are basic examples of associative algebras? Examples. Algebras of polynomials. It's a commutative algebra. The free associative algebra. If something is unclear, please ask questions. Free associative algebra. The next example is as follows. So assume assume V is a vector space, arbitrary, maybe infinite dimensional, and the algebra is the algebra of all operators, endomorphisms on V. And in particular, assuming V is the coordinate complex space, then this algebra is simply the algebra of matrices, of n by n matrices, say complex valued. Now, what are representations? Representations of A associative algebra. So assume V is a vector space, and a representation of A, on V is an algebra morphism T to the algebra of operators V. And some other definition, we say that T is faithful if the kernel of T is reduced to 0, which means that our T embeds our algebra into the algebra of operators on V. And easy proposition is any algebra A has a faithful representation on some space V. How to prove this? So assume first proof. Assume A is unital, which means that it contains unity. Now we define the regular representation. Take as T. Take as T. The regular representation. Regular representation, which this means that the space V is A itself, and the algebra acts on itself by left shifts, meaning that given an element A, the corresponding operator maps an arbitrary element B to AB. And this is faithful because we can apply it. We can apply this to B. 1 implies that T is faithful. And if A is not unital, if it's not unital, then we always can adjoin. Adjoin 1. Okay, so this is the end of the proof. This is very easy. Some questions, maybe? Please ask if something is unclear. Okay. So the next topic is the definition of the commutators. So by very definition, if you have two elements of A, we define the commutator as AB minus BA. Okay. So this is quite obvious, but an easy claim, which is Leibniz rule. Leibniz rule, which says the following. So assume we want to take the commutator of some A, some monomial, certain elements, B1 and so on. And then the result is as follows. We apply A to each of the factors, meaning that this formula we apply A to this element and take the product over the remaining. So this is easy to prove and very important in calculations. Okay, so what next? Next, I would like to introduce the object, which I will denote by Dn. Dn. This is the algebra. Of differential operators. My notation is Dn. So I define it first as follows. I take the free algebra in 2n generators, which I define as follows. This is my notation. Sorry. I take this algebra and take the quotient over the relations annotator is equal to 1. So is it clear what I mean here? So in more pedantic way, I have to introduce the ideal, the two-sided ideal, two-sided ideal generated by elements of a form and take the quotient over this ideal. So what we get is my algebra D. For instance, in the particular case, the simplest case, so then D1 or simply D is the quotient of a free algebra over the relation PQ minus QP equal to 1. So let's, for simplicity, focus on this particular case. So we have a simple claim. So this algebra is the span.
I'm sorry, shouldn't we include some relation between PI and PJ and QI and QJ?
Ah, yes, you are right. You are right. I'm sorry. Indeed. Thank you. Thank you. So the P generators commute and the Q generator also commute. Okay, thank you. So the claim is D is the span of a normal of the normal monomials. Normal monomials are monomials, in my definitions, are monomials of this form. First some power of Q and next some power of P. So this is easy. So for instance, if you, in general, any element of our algebra is the linear span of some monomials in Q and P, and each time we have the two letters P and Q which are written in non-normal order, meaning that we have some P, Q, and we replace it by Q, P plus 1. And using this operation, we can reduce any non-normal monomial to a linear combination of normal monomials. So finally, we get only normal monomials. And the next claim, which seems to be obvious, but actually it's not completely obvious, is that the normal monomials in D are linearly independent. This needs some proof. How to prove this? I propose the following argument. Let's take, this will be our first example of a representation of our algebra on some space. So we take as V the space of polynomials in one variable. And I want to define some representation Define representation of our algebra on the space of polynomials as follows. It's sufficient to define it on the generators. So I take the operator corresponding to P is D, which is the operator of differentiation, and Q, I write it as follows, which is multiplication by X. So it's easy, it's trivial to see that we have these connotation relations. And this implies that T is indeed a representation. And now I want to prove our claim inside the algebra of differential operators. So I want to prove, it's enough to prove, that the monomials of this form are linearly independent. And how to do this? So assume that we have some linear combination. Assume we have linear combination which is equal to 0. So assume we have some coefficients and this is equal to 0. Let's focus on the top degree terms. Focus. Top degree. What means top degree? In this case, top degree with respect to the order of differential operators. With respect to this summons. Some assume that the top degree is some. So assume the top degree is some number, say k. Now apply our operator, I mean the left-hand side, xk. What we get? So what we get that all the summands of lower degree are killed. Their effect is equal to 0, and we look only on the top degree terms, and we get something like this. We get something like this, coefficients multiplied by k factorial, and this one is equal to 0 inside the algebra of polynomials. This implies the coefficients, the top degree coefficients are 0, and we get that our linear combination is in fact zero linear combination. This is the proof. So this is a very simple example which demonstrates how useful is the idea of consider some representations, some realizations of our algebra inside the algebra of operators. And the same way, the same holds for the algebra Dn with notation. Yes, for this algebra. Again, we can consider normal monomials, which means that the q variables are put on the left and the p variables are put on the right. And the normal monomials are linearly independent, which implies that Dn, yes, is isomorphic to the algebra of partial differential operators in n variables with polynomial coefficients. Maybe I would like to just to give some nice definition. I will not use it. Definition is as follows. So assume that A is an arbitrary commutative unital algebra. In my example, A was the algebra of polynomials, but assume it's arbitrary unital commutative algebra, then we can define the algebra of differential operators on A. The algebra of differential operators on A. The definition is very general. It seems it's due to Grothendieck and goes as follows. We define dA as the union of a space. This is the space of differential operators of degree less or equal to n. And the definition goes by induction, recursive definition. First of all, we define what is the first the zero component. These are the operators of multiplication by let me maybe so this is, in other words, the set of the multiplication operators. And I assume that it operates on B. So this is just the regular representation. Some questions, maybe not. And then by induction, by induction, the definition goes as follows. We say that Dn of A is the set of operators on A is a set operators X such that by taking the commutator with any operator of multiplication, we are reduced to the subspace of differential operator of smaller degree. So by recurrence, we define what is this. So this is the general and abstract definition, and some problem exercise is to prove that for a algebra of polynomials, this is exactly the algebra of differential operators, which we discussed above. Okay. So this construction leads us to some general definition of filtered algebras. Filtered algebras. So I recall the definition, what is this? So assume that A is associative algebra. It is said to be filtered if some question, please ask, please. No? Okay. So A is said to be filtered if it is represented as the union of some vector subspaces. Vector subspaces. Sum usually goes formally from 0 to infinity. And the axioms are as follows. So we have, this is some chains of subspaces. The next, what I want, the algebra is unital, and I want the unity must be contained in the component number 0. And the main axiom is that if you take the product, so product some element of degree less or equal to m multiplied by an element of degree less or equal to n, and this is contained in the space, in the subspace of elements of degree less or equal to m plus n. So this is the formal definition. And of course, we need some example, and a good example is our algebra D. Example. So take as A our algebra D. So I recall this is Q over PQ minus QP. And what is the filtration? And actually, there are different ways to introduce some natural filtrations. One is essentially a degree with respect to the order of differential operators, which means that we said that A sub n is by definition the linear span of the normal monomials, and such that L is less or equal to, so this is one definition. First definition, maybe it's better to say first filtration. If you take a realization of this algebra, this abstract algebra, this algebra, maybe it's better to say this is algebra, maybe introduce it in addition. Canonical commutation relations. And another filtration is as follows. The sum of a total degree of a monomial does not exceed n. This is second filtration. And it's easy to see that the axioms are satisfied. The main point is to verify this axiom, but this is very easy. I'm sorry. What happens? Sorry. Okay. Okay. So the next definition I need is the graded algebras. Graded algebras. So the definition is very similar. So a graded algebra is defined as follows. But instead of a chain, a nested chain of subspaces, we want a direct sum. So I want that our algebra is represented as a direct sum of subspaces. Some subspaces. And the axioms are as follows. Again, we want the unity to be in the component number 0. And again, we want this. And what are examples? Of course, the algebra of polynomials. And again, there are different ways to introduce the grading. The most common is to take the grading with respect to total degree. Linear basis is formed by monomials, and we say monomial has total degree, and then it is in this component. Okay. Another example is the algebra, the free associative algebra. Here the basis is formed by words in n letters. Including the empty word, which is by definition the unity. So something like this. Like this. And the degree is the number of letters. Now we need there is some natural interaction between the filtered algebras and the graded algebras. Of course, the graded algebra are a particular case of filtered algebra. So graded algebra contained in filtered algebra. This is trivial because if you have a graded algebra, then we proclaim that the corresponding filtration is the sum of the homogeneous components from 0 to another very useful observation is that construction which to any filtered A one signs a graded algebra, which is usually denoted as GR-A, as follows. In this graded algebra, its homogeneous component number n is defined as the quotient of this type. And the operations are defined in a natural way by taking the representative of elements in the graded algebra. I don't want to go into details. This is a very standard definition. And now what we have, some example. Some examples. So take the filtered algebra, take Dn as a filtered algebra. For instance, with respect to the degree of the total, one can take total degree of monomials, or one can take the degree with respect to the P generators, which means that we consider the degree of differential operators. And then the associated graded algebra is isomorphic to the algebra of polynomials. Algebra of polynomials in twice many variables. One can denote this algebra as maybe why is this? The idea is that we, by the very definition of our algebra, two generators commute modular terms of a smaller degree. This means that the associated graded algebra is commutative. So we have a map. We have a morphism, an algebra homomorphism from our graded algebra to the algebra of polynomials. Save it. I what does this mean? This means that some monomial, if you take some monomial in our generators, in this algebra, we look at the top degree terms. At the top degree terms give us an element, a homogeneous element of the algebra of polynomials. And then we argue that our multiplication is commutative modulo lower degree terms, which gives us this map. And what next? We have to prove that this map is an isomorphism. It is surjective. This is evident. And we need to check that the kernel is zero. The map is injective. And this is just another formulation of the fact that the normal monomials are linearly independent. And using this fact, we can conclude that this is indeed an isomorphism. And this works for another filtration. If you take the filtration with respect to the total degree, the argument is exactly the same. Okay. Now we come to the second part of my talk today. Lie algebras. So Lie algebras. The formal definition, let me recall it, is Lie algebra G I will use the Gothic letters. So is the Lie algebra. Which means it is a vector space. Field. But I will write simply C, but it can be arbitrary field. And there is some bilinear map. Which is called bracket. Which satisfies two axioms. Skew symmetry which means that xy is equal to minus x. And the Jacobi identity. Which means as follows: for any triple x1, x2, x3, the following relations holds. We take the commutator, the double commutator, the double, maybe not commutators. We applied the bracket twice. And then we take the cyclic permutation of the letters in some order. The order is unessential, for instance, like this. And the term is the relation, it must be equal to 0. So this is a formal definition. And now there are some examples. Some examples. First, so assume A is an associative algebra, and the bracket is the commutator. Then this operation turns our associative algebra to a Lie algebra. This is the Lie structure of an associative algebra. So the axioms are verified directly. The first axiom, skew symmetry, is obvious. And the Jacobi identity, a little calculation shows that it is satisfied. The next examples, for instance, in particular, we can take the algebra of matrices or endomorphisms of some vector space, say C, and the corresponding Lie algebra is the general linear Lie algebra, which is simply the algebra of matrices. It is denoted as follows. And it has a basis, a natural basis, matrix units. This is the matrix with 1 at intersection of row number I and column number J, and all other elements B equal to 0. And then we have the commutation relations, the brackets between two basis elements look as follows. Concar delta minus this follows from the multiplication rule for matrix units. It's easy to verify. Okay. We have a notion of Lie subalgebra. Lie subalgebra. If J is a Lie algebra and H vector subspace, then it is a Lie subalgebra if taking the brackets, H is stable with respect to the operation of taking the bracket. Okay? So, for instance, when there are plenty of Lie subalgebras in a general linear Lie algebra. For instance, the Heisenberg algebra, simplest, three-dimensional. It has the basis of three elements. X, Y, and Z. And the bracket is as follows. X and Y gives Z, and Z is in the center. He is the center. Meaning that commutators, the bracket, sorry, is equal to 0. And we can embed this Lie algebra. It's easy to see that it is indeed a Lie algebra, that is the Jacobi identity satisfied, and this can be obtained directly from the realization of this Heisenberg inside the Lie algebra of matrices of order 3. Namely, you have a matrices of the following form. This is X. This is Y. This is Z. So this is the Lie algebra of strictly upper triangular matrices of order 3.
Извините, а можно такой телеологический вопрос в целом? Ну вот, мой вопрос звучит примерно так. А есть ли какая-то формулируемая причина, почему скобка на алгебре Lie является дифференцированием себя? То есть, наверное, правильный вопрос задать, что такое дифференцирование. Мне кажется, самый правильный ответ на это то, что это гомоморфизм из алгебры в расширение с квадратом 0. с целью, где модуль — это цель дифференцирования.
Подождите, Денис, я, может быть, до этого дойду, чтобы
Хорошо.
потихонечку мы до этого доберемся.
Ну, я подожду. Хорошо.
And more generally, we have the Adjoint theorem, which says the following: if G is finite dimensional, it can be embedded into some GLM. It can be realized as a Lie subalgebra of some GLM. In other words, one can say as follows. This is a non-trivial result. And there are a number of demonstrations of it. But in order to discuss it, let me recall one more definition, what is a Lie algebra representation. Algebra representation. So this is simple. We take on some vector space. We have some vector space. Some vector space. We consider the space of operators with the Lie structure, which is given by the commutator. And T should be a morphism to this Lie algebra, the Lie algebra of operators. Which means that T is a linear map, which is consistent with our structure. So if we apply T to the bracket of some two element, what we get is the commutator of the corresponding operators. And the next observation is that to any Lie algebra, we can assign some canonical linear representation, which is called the adjoint representations. Adjoint representation. Namely, we have some Lie algebra, and we take as V G itself. And our representation, which is denoted as at the operator, which corresponds to some element X, is defined as follows. It acts on a given element Y by taking the bracket. This is the definition. And the fact that this is a representation, is a representation, is equivalent to the Jacobian identity. This is a little problem. To check this. So this shows why the Jacobi identity is a crucial property, a crucial fact. And there is some little consequence of this. If they suppose that the center of G is trivial, this implies that our adjoint representation is faithful. Its kernel is equal to 0. This is, I think it's obvious, which shows that the other theorem in this situation, when the center is trivial also. So the non-triviality of other theorem is related to the fact that in general, a Lie algebra can possess a non-trivial center. So I would like to mention some remark. So the remark is there is some similarity. There is some similarity between regular representation of an associative algebra on itself and adjoint representation of a Lie algebra, on itself. Only in the first case, in the case of an associative algebra, it's easy to see that the regular representation is faithful for unital algebra. For the Lie algebra, the difficulty arises from the center. Now I have time to come to the next topic. This is the universal undeveloped algebra. So assume that, let me give the definition in the case that our Lie algebra G is finite dimensional. So assume, for simplicity, that the dimension is finite, and take a basis. Take basis. In G, and consider the structure constant. Structure constant, which are related to our bracket, which means that we take the bracket of any two basis elements, and this should be some linear combination, right? This linear combination. So these are some coefficients. So this is just some display for the bracket. And then the definition is as follows. The associative algebra which which is called the universal untitled algebra of our Lie algebra, is defined as follows. We take first the free algebra with n generators. And we take the quotient over the relations for any so some examples. If our bracket is trivial, so the structure constant are equal to 0, then what we get the algebra of polynomials in n variables. So this is G is commutative for abelian, meaning that bracket is identically equal to 0. This means that G is equal to the algebra of polynomials or one also say that in this case G, okay, I will say it a bit later maybe. Okay, that U of G is simply the symmetric algebra, of our vector space. There is nothing except the vector space structure. The next case is, say, assume that G is the Heisenberg. So we have a generator X, Y, and Z, and the only non-trivial bracket is this one. Then we can realize our universal untitled algebra. We can realize, G can be realized inside the algebra of differential operators in two variables. And this is done as follows. X goes to, so we have, what is this? I recall that this is the algebra of have P1, P2, Q1, Q2. Modulo the relations, the P1 and P2 commute, Q1 and Q2 also commute, and we have a quantum mechanical commutation relations. I, J. So, and then you can set as follows. X goes to P1, Y goes to Q1, Q2, and Z goes to Q2. And one can verify easily that this element commutes with this and with this. And if you take the commutator of this and with this and apply the Leibniz rule, the commutation with this no effect because they commute, and the bracket of this element and this one produces 1, and so the result is Z. And one can easily show that this is indeed the universal envelope algebra of a Heisenberg. And the more general, some more general way to define the universal envelope algebra is as follows. Say, take T of G, the tensor algebra, which means the ground field, plus G itself, plus the tensor of G with itself, plus the triple tensor space, and so on, so on, and so on. And this is an associative algebra. And actually, this is a free algebra. If we take a basis in G, what we get is a free associative algebra. And now the definition is as follows. We set that U G is by definition as follows. We take the tensor algebra, and again we take the quotient over all relations of this type. So here, it's important to understand. So the left-hand side is the commutator in the tensor algebra, and the right-hand side is the bracket in G. This is the formal definition, which is applicable to any Lie algebra of finite dimension, of infinite dimension, any field of characteristic 0 or characteristic P, no problem, quite a general definition. So assume if you know what is a Lie group, so assume that the base field is R, and our Lie algebra is the Lie algebra of a Lie group. I assume that we know what is this. Then one can show, this is the Laurent-Schwarz theorem, I think it's correct. It says that the universal enveloping algebra of a Lie algebra of a real Lie group is formed by left invariant differential operators. Differential operators on our Lie. There is another version of the same result, which is a bit different, but actually it is the same, which says the following. So U of G can be also realized as the algebra of distributions. Assume that we know what is a distribution of a real manifold, and the Lie group is a real manifold, so the notion makes sense, which are concentrated at the unit element of our Lie group, and the product is the convolution product of distributions on the Lie group, which is well defined because the support is a single point, and the convolution product is well defined for distribution for compactly supported distribution. So if you know these notions, you can understand the meaning of this result. This is very important result. This is very important result. And actually it works not only for really algebra, but it also works in the setting, more general setting of analytical groups, something with other generalization, formally groups. Okay, I don't want to continue. And the next factor I would like to mention is the universal property. Universal property, which is a formal consequence of a very definition of our object. And the universal property says the following. So assume that we have a morphism of Lie algebra. This is G to some associative algebra, but which is equipped with its canonical Lie structure. So we have a bracket which comes from the commutator. Then, first of all, there is some canonical map to our universal undeveloped algebra. By the very definition, we have a map from G to this algebra, and the claim is that there exists a unique algebra morphism. This is an algebra morphism which makes this diagram commutative. So in particular, which means that any Lie algebra representation in some vector space gives rise to a representation of a universal undeveloped algebra on V, and vice versa. If you have a representation of an associative algebra, it gives us a representation of Lie algebra. And this is very important. This is very important because if you want to study Lie algebra representations, we can pass to representations of associative algebra, and the universal algebra have more structures. It is richer than the Lie algebra, and its role can be compared with the role of a group algebra in group representation theory. If you want to study representations of groups, it's very useful to use group algebras. So the role of the universal undeveloped algebra is quite similar to the role of a group algebra in group representation theory. And what next? The next topic is the Poincaré-Birgoulet theorem. I don't want to discuss it in detail. We will begin the next talk with Poincaré-Birgoulet, but I only would like to explain very briefly what is this. The Poincaré-Birgoulet theorem. The meaning of this result is that it says us what is the size of a universal undeveloped algebras. And very roughly speaking, it says that, roughly speaking, the Poincaré-Birgouwit theorem says that the size of if dim. This is very rough formulation. Is finite. Is the same as that of the algebra of polynomials and variables. This is a difficult theorem, but actually there is a simple proof for GLN. Simple proof for GLN. And in the next lecture, I will describe this simple proof for GLN. And it gives actually much more. It gives much more because actually all finite dimensional Lie algebras are subalgebra of GLN, and as a corollary we get for nothing the Poincaré-Birgouwit theorem for all finite dimensional Lie algebras. Of course, modulo the other theorem, but in practice, the finite dimensional Lie algebras are already realized as subalgebra of general linear algebra, so we can prove rather easily the Poincaré-Birgouwit for finite dimensional algebra. So this will be the next topic for the next lecture. So that's all for today. So please ask maybe some questions. You can ask in English, you can ask in Russian, of course. I apologize because what is the textbook? Oh, actually, my course is not about Lie algebras. It's about universal undeveloped algebra and Yangians. So there are many textbooks about Lie algebras. You can just Google for Lie algebras. Fundamentals of Lie algebras. Okay, what are the books for? There is a nice book by Kirillov Jr. Humphreys, if you want, and many books about Lie algebras, many books. And by the universal undeveloped algebra in general, there is a very nice book by Dixmier, which is just called Universal Undeveloped Algebras. It exists in French, in English, in Russian. But this is a very detailed book which contains many things which I will not discuss. And finally, there are my topic is Yangians. And about Yangians, there is a book by Molev, Classical Lie Algebras and Yangians. It is mentioned in the annotation to my course. So for me, the basic reference is the Molev book, and there is also some survey paper. By Molev, Nazarov, and myself in Успехи математических наук, Russian Mathematical Surveys. Can be easily found in this easily open access. So, okay, so these are the main references. Maybe something else?
Я хотел, собственно, спросить, вот вы считаете, что как бы, факт того, что присоединенное представление является представлением, это и есть как бы, объяснение того, почему умножение является самодифференцированием. И это как бы такой конец ответа.
Подождите.
Да.
Я немножко не понял.
Ну, я вот задавал там, возможно, чересчур философский вопрос. Вы сказали, что ответ на него будет. Я посчитал, что как бы...
Да. Но ответа вы не дождались. Да, так еще раз повторите, пожалуйста, вопрос.
Ну, правда ли, что ответом должно считаться то, что регулярное представление присоединенное является представлением? Это вот как бы должно являться объяснением этого факта или нет?
Объяснением чего? Тождество Якоби?
Ну, я бы предпочел называть тождество Якоби, что скобка дифференцирует себя при композиции.
Что значит скобка дифференцировать себя при композиции?
Выполнено тождество Лейбница для оператора ad x, для любого x.
Ну да, я согласен. Ну да, можно так считать, что тождество Якоби происходит отсюда. Но можно считать также и то, что тождество Якоби выполняется в ассоциативной алгебре.
Но это как бы комбинаторное объяснение, а мне хотелось бы иметь скорее геометрическое в каком-то смысле. Непонятно, правда, насколько оно может быть геометрическим, но...
Не знаю. Тут есть некоторая как бы загадка. Ведь можно брать, если у вас есть алгебра, просто алгебра, вы можете брать коммутатор, вы можете брать антикоммутатор. Не АБ минус БА, а АБ плюс БА. И если смотреть тогда на антикоммутатор, на эту операцию, то что получится, если вы хотите потом аксиоматизировать...
Получится, конечно, Йорданова алгебра, да.
Йорданова алгебра. И, казалось бы, какая, собственно говоря, очень похожая. Алгебра Ли и Йорданова алгебра. Ну, Йорданова алгебра, конечно, тоже вещь вполне, так сказать...
Но я бы сказал, что там совпадения заканчиваются, когда заканчивается конечномерность. Потому что в конечномерности они обе эти структуры имеют отношение к нидипотентным ассоциативным алгебрам в некотором смысле, но как только начинаются бесконечномерные алгебры, там Лиевские и Йордановы расходятся совершенно в разные стороны.
Ну, видите, они на конечном уровне, они как-то расходятся.
Ну, они все-таки, там можно их упаковать в несколько общий фреймворк, того, чем там Голод занимался когда-то.
Ну, может быть, я этого не знаю. Но по моим понятиям все же Йорданова структура интересна, но гораздо менее интересна, менее содержательна, чем Лиева структура. И главный аргумент в пользу Лиевой структуры, который так сразу не видно, почему это так, связан с тем, что за Лиевой структурой стоят группы Ли, а за Йордановой структурой такого рода объекта нет. Вот, собственно говоря.
Это, я бы не сказал, что это является математическим утверждением.
Это не математическое утверждение.
Да, но, возможно, просто люди недостаточно внимательны к структурам, которые не являются бинарными операциями на множестве.
Ну, может, не знаю.
Ну, ладно.
Ну, хорошо. Значит, я тогда хочу еще
Стоит
раз
закончить философию. Извините.
еще раз повторить просьбу, что для того, чтобы иметь какую-то обратную связь и посылать домашние задания для тех, кому это нужно, я попрошу просто прислать мне вот это коротенькое, значит, имейл с указанием, просто чтобы я понимал. И, кстати, я еще буду признателен за возможные, так сказать, замечания. Для кого-то то, что я буду рассказывать, будет слишком легко или, наоборот, слишком трудно, тогда я буду, соответственно, как-то менять стиль своего изложения. Потому что мне было не очень понятно, понимаете, как бы, как аудитория воспринимает то, что я вот сегодня рассказываю. Там для Дениса то, что я говорю, все это абсолютно понятно и тривиально. Для кого-то, может быть, это вдруг, наоборот, какие-то вещи трудны. Просто мне важно иметь какую-то обратную связь. Так что поэтому, пожалуйста, присылайте ваши какие-то замечания на этот счет, я тоже буду признателен. Ну вот, хорошо. Значит, домашние задания тем, кто откликнется, я тогда в самом скором времени пришлю. Есть еще, может быть, какие-нибудь вопросы? Ну, хорошо, тогда на сегодня все. Спасибо, до свидания.